So we've learned by looking at the spectrum of a star, you can learn a lot about it. So by finding the peak wavelength, then you can find the temperature of the star. By looking at the spectral lines, you can figure out the chemical composition. By looking at the shift in the spectral lines, you can find out how fast the star is coming towards you or going away from you using the Doppler shift. All those are looking at the spectral characteristics of the star. Further spectral characteristics, looking at the spectral lines, can tell you a little bit more about the star. It might give you an estimate of the luminosity of the star, and so that would be useful as well. There's a limit to how much you can learn from the spectrum of the star. Even though it's an enormous amount, there's a couple of things you cannot do by looking at the spectrum. For one thing, you can't tell how much a star weighs. To do that, the only way that we have of measuring the masses of stars is that we have to have binary stars, and as the stars are moving around, we measure that motion. Johannes Kepler, 1600s, worked out that for a planet going around the sun, p squared equals a cubed, where p is measured in years and a is measured in AU. So a would be half of the longest distance across the elliptical orbit. So usually the elliptical orbit, one side gets close to the sun, one side farther away, so half of that is going to be the average distance. All right, so Isaac Newton realized, well, really it's total mass times p squared equals a cubed. Okay, again, total mass measured in solar masses. This is still measured in years. That's still measured in AU. Okay, so solar mass. What's a solar mass? What's how much mass the sun has? So if you come up with, if you do some algebra, and you've got total mass equals a cubed over p squared. So again, a is measured in AU, and p is measured in years. Okay, now this becomes a little bit problematic because obviously if you watch the stars go around and it takes 25 years to go around, then it's pretty easy. P is 25 years. If, on the other hand, you see stars going around and it only takes 7 days, you got to convert 7 days into years. Well, 7 days is not much of a year, so you take 7 divided by 365, and that would give you how many years it is. And then you square that, and that would be what goes here. And then A, you got to figure out how many AU it is. Well, it's hard to figure out how many AU it is because you're looking at something that's light years away. And so you have to somehow figure out the distance in AU between the two stars. Okay, to do that, you've got to somehow figure out the distance between the two. And then it actually turns out to be pretty simple, that the separation in AU, as it turns out, is just equal to the distance in parsecs times arc seconds. But won't worry about that just yet. But if you can do all that, you can find the total mass. Okay, now that's not the mass of each star, but it's the total mass. So if you get a total mass of 2, that means that both stars have to add up to 2 times the mass of the sun. If you get a total mass of 1.2, that means the mass of one star plus the mass of the other star is 1.2 times the mass of the sun. All right, so what we do is we start doing this and measuring masses of stars, and with spectroscopic binaries, it's pretty simple because you can figure out how much mass each star has proportionately, and then so then you can figure out the individual masses, and then you decide, if you look at other kinds of binary stars, that a star just like one that was in the spectroscopic system is going to have the same mass. And so one thing you discover is, if you look at main sequence stars, and this is only true for main sequence stars, what you discover is there's a relationship between how bright the star is, the luminosity of the star, and the mass of the star. And so that means if you can figure out the absolute magnitude of the star, then you can figure out the luminosity. Remember, there was an equation for that. So you could figure out the luminosity once you have the absolute magnitude, and then come over here and drop down, and that would tell you the mass of the star. You know, if your luminosity was here, come over, come down, that would tell you the mass of the star. Okay, and so that's the mass-luminosity relationship. One interesting thing, on the HR diagram, remember the main sequence runs diagonally. So if we graph absolute magnitude of luminosity here and temperature or B minus V or spectral type here, you get something that looks like this, diagonal. Well, this is more luminous, therefore more mass. And so what that means is on your HR diagram, you have more mass up and to the left. Okay. And so that turns out to be a very useful sort of thing. So that means we can now figure out masses of stars. So the first 3 stars on this list are all main sequence stars. Remember, Roman numeral 5 means main sequence. So the question is, which of these stars has the most mass? Think back to the previous slide. HR diagram, upper left is the most mass. Well, left, the farthest to the left is O, and then B, then A. So Fomalhaut has the most mass of those 3 stars right there. Which one has the least mass? Well, that would be Wolf 358. Okay, and so this is kind of how you think about it. So let's remind ourselves. Okay, so let's remind ourselves about the HR diagram. So we have the HR diagram. The main sequence runs kind of like this. So to the top is brighter. Towards the bottom is dimmer. Towards the right is cooler. Towards the left is hotter. Towards the upper right is bigger. Towards the lower left is smaller. Towards the upper left is heavier. So that's more mass. Towards the lower right is lighter, so that means less mass. Okay, and so what you know is that this is O, B, A, F, G, K, M across here. We know the absolute magnitudes get bigger going down. Okay, so absolute magnitudes. And then we also know, however, that everything on the main sequence is Roman numeral 5. And we know up here are Roman numeral 1A and 1B. And then we have 2, and then we have 3, and then down in here is 4, okay? And so what you can do is you can then, when you are looking at that table of data, you can imagine at this diagram right here. And in fact, I often have students, you know, this is the first thing they do is they take a test, and they draw this diagram right here, and then they imagine when I ask which star is hotter, which star is cooler, which one's bigger, which one's dimmer, which one's, brighter, which one's, more mass, which one's less mass. Okay, now remember the mass idea, mass only works along the main sequence. It doesn't work on anything else. Okay, so you cannot really say anything about mass for stars that are off the main sequence, but you can about things on the main sequence. And so what our students will do is they'll start off with this diagram right here, and they'll say, oh, okay, you can just imagine taking that chart, that table of data, and then imagine where stars would be on here. And so you imagine where stars would be on here, and then it's pretty straightforward. by where they would be as to how to answer the question. And so that's the idea. It's just you either just mentally and imagine where they are, or physically just draw this out and put dots about where the stars would be, and then it makes it pretty easy to answer the questions. All right, so now we know about masses of stars.